Let's consider another application of lifting objects. On the previous video, we talked about lifting objects where they stayed a constant weight and we lifted them up and to a fixed distance. So we talked about picking up a backpack and lifting it up onto the counter or um, something of that nature. So when we calculated the work needed to do that. But what if we wanted to compute the work to lift objects or to pump fluid, which is really lifting an object. It's lifting a fluid object, but it's lifting an object from a container. So let's think about that. How much work would be done if our force varies? So let's think about that. If we had, again, let's just do a quick review of force. Force is going to be mass times gravity when we're working in the metric system. So force is mass times gravity. When we're working in the US customary system, remember that force is measured simply as a weight, a pounds. But in the metric system, it's going to be our mass times our gravity, and we know that mass is the density of the object times the volume. So we can continue to break down that force. Force becomes mass times gravity, or density times volume times gravity, where our density and our gravity are constants. What could vary is the volume of the object that we're lifting. So let's go ahead and highlight that formula and then talk about how are we going to set up a lifting problem. And I think before I do, let me see if I can get my little picture on the same page as this. There we go. I'm going to talk about a pumping problem, but lifting is going to be calculated in the same sort of way. If we were lifting an object like, say, a chain over a building or something of that nature, it's going to be calculated in the same way. It just won't be a fluid that we're moving. It would be an object that we're moving. So in this case, though, let's suppose we have some sort of container. I drew kind of a funky little picture over here. It's just a little container. It's the way I drew it. It's half full of water. And say we wanted to pump that water up and out of this container. If we want to do that, what we're doing is we're actually lifting slices of water. So I'm going to draw a slice of water. Now, of course, when we pump it, that slice doesn't stay in its form, but we're thinking about taking this slice of water and we're thinking of moving it up and out of the spout. So we're taking that water, lifting it up from this position. We have to think about how far we have to lift it, how much work it takes to lift it up to the top of that spout and out. Okay, so that's what we're thinking about. We're lifting slices of water. So we're thinking about lifting slices of water in this scenario. Now, if we were lifting, I could draw another picture if I had a building, and we'll do examples of both of these on this video. But if I had a building and say I had a chain that was hanging over it, it could go all the way to the end, or it could stop right here. It could even have a little weight on the bottom of it. Let's suppose that we were talking about lifting a chain or even an elevator on the inside that is connected by a chain. If we were talking about how much work is needed to lift that chain, and if it had an object on it, the object all the way up to the top of the building. What we're going to do is we're going to think about taking a little slice of that chain, like right here, and we're going to think about how much work is needed to lift that little slice up to the top of the building. So we would be thinking of lifting, instead of a slice of water, lifting a slice of chain. Okay, if it was a chain. So this theory works whether we're talking about pumping something fluid, because we can think of those as slices of water, or we could think of it as lifting something solid like a chain, because we're going to divide that chain up into little pieces and lift it up and over the top of the building. Or if it's an elevator, lift it to the top of the building. Okay, so when we set up these lifting problems, what we want to do, let's zoom in again, what we want to do is we want to set up an axis that makes sense in the context of the problem. So just as a note, you will see in my work, I tend to like to set up a vertical y-axis. I tend to like to set up a vertical y-axis, basically overlay my rectangular coordinate system on top of whatever shape I'm looking at, whether that's that's some sort of orifice that's holding water that I'm pumping out of, or if it's a building, I tend to set up the rectangular coordinate system as normal so things kind of work out the way I like. So it makes sense in the shape of the object, and I tend to place my origin where it's going to make the most sense in my setup. Then I assume that the interval from C to D is representing the vertical extent of the object or the fluid, where the fluid is contained. And I determine the shape and volume of a cross-sectional slice. So I should keep my force formula up there. So if we remember that force is rho times gravity, because of course we have to think about the density of the object that we're moving, the density of the water or gasoline, or the density of a chain if we're lifting a chain. So the force is going to be the density times the gravity times the volume of whatever that little cross-sectional slice is. So we're going to think of our volume as an area times a thickness. So the area of a slice times the thickness of a slice. If we're slicing, of course, this is if we're setting it up, as I mentioned, across the y-axis. Then I'm going to determine the distance I have to lift each slice, because remember, our work, so why are we talking distance? So force, remember, is going to be the density times the gravity times the volume, which of course the volume is variable. So that's why we're thinking about the variable, whereas these two are constants. So those will just kind of float along in my integral, but this volume could vary. It doesn't necessarily have to, but it could vary, that variable. Now, why are we thinking about distance? Well, remember that when we get to work, and again, we're going to be calculating the work needed to do this. Work is force times distance. So now we're thinking about, okay, we've talked about how do we find the force, how do we find the distance? So now we have to think about, for each slice, which we've calculated the force of each slice to move each slice, now we need to think about the distance we have to move each slice. And so the distance to lift the slice we consider based on where the axis is. Then we simply set up the work integral to lift the slices from C to D. So the work needed to calculate, the integral needed to calculate the work to lift a slice is without the integral. It's just rho times gravity times the volume times the distance lifted. But when we're talking about actually lifting n slices, then we take the limit as n goes to infinity. So remember, what we're doing here is we're dividing up, again, I won't go back to the Riemann sum, but what we're doing is we're dividing up our solid or our volume of water. We're dividing it up into n slices. We're considering the work to move each slice, then we're adding all those slices up and taking the limit as n goes to infinity. So this work is coming out of having taken a look at the total work, is coming from a Riemann sum that turns into an integral. It's the sum from I equals 1 to n of the work of each individual, work sub I, of each individual slice. So this is the work to move each slice. But then, of course, we add them all up, and that is giving us this integral from C to D of the work. And we've talked about how to calculate the work, and we get that integral. So that's the overview of what we're going to be doing here, but the process is going to be the same. We'll set up our axis, we'll determine the interval that we're working with, then we'll determine the shape and the volume of a slice, and then the distance, and we'll multiply the force times the distance. We will have those constants of density and gravity. As long as we're working in the metric system, we'll have those forces of density and gravity, and then we'll just add up all those slices, giving us an integral. All right, so let's take a look at a couple of examples. Okay, so let's consider this. Let's determine the work that is needed to lift. Now, I did say lift, but you know, it is kind of funny. We don't really normally think of lifting water. We think more of pumping water. So maybe it makes more sense to say pump water out of a cylinder with a radius of 5 meters, a height of 10 meters, and it has a spout that is 5 meters above that cylindrical drum that is holding the water. Now, we are going to consider a couple of options. So we're going to consider the option where this cylindrical drum is full of water, so let's do that first. And then we can come back and we'll think about it. What would it be if we only wanted to pump the top half of the water? We'll consider full of water and let's pump it all out. We can do all kinds of variations here. Let's pump out all of the water. So let's consider what this looks like. So we have a cylindrical drum, it's holding water. We'll assume that it is straight up and down, not on its side. And so we've got something that looks like this. It does have a spout out of the top of it that is an additional distance that has to be lifted, but we will assume there's no water in the spout. Let's see, the spout is 5 meters above the top of the drum itself is 10 meters high, and the radius of the drum is 5 meters. So we've got a drum that looks something like this. We're assuming it is full of water, so the water is full all the way to the top of this drum. And just draw it like this, all the way full. And we want to pump water out of this. So the first thing that we have to do is we need to put a coordinate system on this. So what I'm going to do is I'm going to go ahead and I'm going to overlay the rectangular coordinate system with the origin right at the bottom of the drum. And I do think that that makes the most sense. You know, depending on how you set up the origin or the rectangular coordinate system, you could put this in the center of the drum. You could put it at the top of the drum. I've seen variations where like the positive x-axis is always going down like this, positive x-axis. I've seen all kinds of iterations on how to set up the coordinate system, but just to mention that you could set it up differently than I do, but I prefer to set it up this way. And so this is 0, this at the top, because we're 10 meters high, this is 10, and the top of the spout would be 15 on my rectangular coordinate system. And I'm going to be talking about taking a slice of this water and thinking about how much work is needed to lift a single slice. So here's a slice. By the way, the thickness of this slice, I'll give it, I guess, a little bit of thickness. It's going to get infinite, the slices are going to get infinitely thin ultimately, but the thickness here is a delta y. So how much work is needed to lift a single slice out? So let's think about work. First, let's talk about work just to lift a single slice, and then we'll get it into the integral when we add all of those works up, the work to lift all of the slices. So the work to lift a single slice. So remember that work is force times distance. So we could go back to the formula, but I'm just going to derive it again right here. So the work is the force times the distance, and the force is going to be the mass times the acceleration. Keep carrying distance down. And mass is going to be the density of this water, which, by the way, we didn't talk about that over there, but the density of water, density of standard water is 1,000 kilograms per meter cubed. Now, that is standard, and you can use that at the very end. We can plug that in. I will carry my constants throughout. Like, I'm not going to go ahead. We're going to also have a gravitational constant, which we will use 9.8 meters per second squared for the gravitational constant. But because these are constants, you will see in all my work, I wait till the very, very end to plug those in. So if we needed an approximation, then we can plug those in at the end, but I will carry those throughout the work. So it's going to be the density of water, because we're talking about pumping water, times the volume, V for volume, and acceleration is going to be that gravitational constant. So I'm carrying all my values down here. Now, these two are constants, and so in the work, I'm going to pull those out. That's the density of the water times the gravitational constant times, now what is or could vary is the volume of a slice. So, and it's going to be in terms of y. So the volume of a slice is y. And then the distance that we have to lift each slice. So we're going to write that as d of y. So this is the volume of a slice. And this is the distance we have to lift each slice. So we've got volume and distance. So we've got to figure out how to represent the volume of a slice and how to represent the distance of a slice. So let's talk about that in the context of the problem. So here is our slice. We already drew it. The slice is going to be a circle. And the circle, you know, think about each slice. The circles, the area of each of those cross-sectional slices are going to stay the same. That's a constant 5 just because of the shape of our, based on the shape of our cylindrical drum here, those slices are all going to be circles with a radius of 5, and then their thickness is a delta y. So when we're calculating the volume of every slice, let's go ahead and carry this down. I'm going to bring my work down. So the work for a slice, we had some theory in there, but the work for a slice is The density of water times gravity times now the volume of each slice is going to be pi times the radius of each slice, but the radius is not changing for this shape. So that's going to be pi times 5 squared times delta y, the thickness. That's the thickness of each slice. So that's the volume. And how far do we have to lift each slice? Well, each slice has to come from where its position is, which would be at a y value. Let's grab my red pen. So at any given slice, say that's y, when we take that slice, we have to lift it from that point up and all the way out of this spout. So remember, we're not just lifting because the spout was 5 meters above the top of the cylinder, we have to lift it not just from where it was at, but we have to lift it all the way up and out of the spout. And so what we end up getting for the distance of each slice has to be 15, because the top of the spout is at 15, minus where we took the slice, so minus y. So the work for each slice, if we simplify that down a little bit, is going to be those constants, rho of H2O, the density of water, times gravity, times pi, times 5 squared. I'm going to go ahead and move the delta y to the end. 15 minus y times delta y. Now that is the work for each slice, and I do think that it helps when we're setting up these work problems to write the work in terms of a single slice first, and then we can think about, okay, so if this is full of water, that's how much work is needed for each slice. If this container is full of water and I want to pump out all of the water, so let's do part A. So if I want to do all of the water, then the work needed is going to be the integral from, well, we're going to start taking our slices at 0. There's water filled all the way up to 10 in my coordinate system, and I need to integrate rho of H2O times gravity. Now remember, I'm jumping over the sum of each of these slices and letting n go to infinity. I'm jumping straight into the integral, but that's why we're getting to use this formula, times pi times 5 squared times 15 minus y dy. So our delta y becomes a dy when we take the limit as n goes to infinity. And now I'm in the world of integrals, and I can calculate this integral. We've got a lot of constants right here, so I'm going to go ahead and move out the constant. So we've got rho of H2O times gravity. Remember, we can plug those constants in just like we can plug in pi after I've integrated. This is going to become the integral from 0 to 10. This becomes 25 pi times 15 minus y dy. Those are also constants, so let's pull all of this out. Oh, I'd already pulled out the pi. But 25 is also a constant, so let's pull that 25 out as well. So we get 25 rho of H2O, gravity, times pi, all a bunch of constants. When I integrate 15 minus y, I get 15y minus y squared over 2. I'm evaluating that from 0 to 10, so we end up with 25 rho of H2O times gravity times pi. When I plug in 10, I get 150 minus 100 minus 50 minus 0. And we end up finding that the work is, that ends up being 100. So we get 2,500 pi times density of water times gravity. And that would be my answer. That is in joules, if we want units on it. That is in, whoa, that is in joules, and that answer would suffice. That is in joules of work needed to pump all of that water out of this container. But if we really wanted to, we could pull out our calculator, we could plug it in. Let's see, let me pause it and I'll plug that into my calculator. Okay, so I plugged it in. It ended up being a really big number, 76,969,020 joules of work. So we could say it's approximately 77 million joules of work. But again, my highlighted answer, I actually prefer that highlighted answer, and that's what I would expect you to do. Now, let's just do one little variation on this. Let's suppose that we wanted to do the same let's do this same exact container, but let's just say we wanted to pump out half of the water. So what would be different if I wanted to pump out, we could do all kinds of variations on this, but what if we wanted to pump out only half of the water? So if we wanted to pump out only half of the water, we've actually done a lot of the work. It's funny. We've done a lot of the work to calculate work. But if we only wanted to pump out half of the water, so if we want to think about that scenario, if we're only pumping out half of the water, if I could go back, I'm trying to keep my picture on the screen here. If I came over here, if I only wanted to pump out half of the water, then we will assume obviously that we pump out the top half first. So then we would be integrating from 5 to 10. So the only variation that we would get if we wanted to pump out half of the water, and again, we will assume that we're pumping, of course, that's how you pump things. You pump the top half and then you pump the bottom half. So we're pumping out the top half of the water. So the only difference here, we don't have to go through, it's the same slices, it's the same scenario, it's the same container, it's the same spout. So if we're pumping out only half of the water, it would be the integral from 5 to 10. That's the only variation here of the density times the gravity times pi times 5 squared times 15 minus y dy. And I'll just leave it there, but I just wanted to highlight that, with that iteration, if we only wanted to pump out half the water, then we would be calculating the work to pump from 5 to 10. And we could do other variations, like for instance, if we wanted to say, what if it was only half full? Well, if it was only half full, so let's do C. If it was only half full, what would change? Well, if it was only half full, then we would only be integrating from 0 to 5. We would, right, of course, the top half of the container would have no water. So if we're pumping from 0 to 5 of rho of H2O, gravity, times pi, times, right, and I'm just rewriting each of those out again, dy, and of course you simplify, pull all the constants out, and then integrate. Okay, let's take a look at another scenario. And I think on this next one, maybe we will just set it up. Okay, let's take a look at another one. Let's determine the work that is needed to pump gasoline out of a circular drum. And I drew it below. This is actually one that is in the book, and it has like a nice little image of it and thinking about pumping out of this. So let's suppose that we want to pump out this gas, so it's on its side, and we want to pump the gas out of this circular drum, and it has a radius of 5 meters, and it has an outlet at the top. So there's no spout. We're literally just, let's think of this as being the outlet right here. And somehow there's obviously some way, let's just put like a line down. There's some way here in which we can pump this gasoline up to the top of this spout. Or there's no spout, sorry, I said spout, but to this outlet. Let's call it an outlet. So it looks something like this. And obviously the density of gas is a little different than the density of water. So I would give you, if we're working with some other liquid, of course I would give you the density. So we know the density of water is 1,000 kilograms per meter cubed, but the density of this particular gas is 737 kilograms per meter cubed. And this is the image of the cylindrical drum. We've got a 10-meter length, and it's a cylindrical drum on its side with a radius of 5 meters. So I wanted to do this one because, again, the first thing we have to do is think about how do we want to set up our coordinate system here, and then think about what the volume and the distance to lift each slice is to calculate our work. So in this case, what I would do, and this is one that's a little different. I wouldn't actually put my coordinate system at the bottom because I see this circle right here, and I'm thinking to myself, I'm going to need to set up an equation to think about that circle and how that changes the thickness or the width of each of the slices of gas. So I'm going to actually put, because I'm working with a circle and it is pretty specific to circles, I am going to put my coordinate plane right at the center of this drum. So there's my X and my Y axis. The reason I'm doing that is because now this end cap of the cylindrical drum is now in the shape of a circle, and I can write the equation of that circle. X squared plus y squared is actually equal to 25. So I can write it in that way. If I had put my origin at the bottom, then I would have had to shift my circular equation. I would have to, of course, adjust for the center, which you could do, but I just don't feel like doing. So now let's think about, and I'm going to grab kind of that gold color that I used for the gasoline. Actually, that might be hard to see. Let's use red. So I'm going to go ahead and grab my red pen, and let's think about, now what we're doing here is we're going to be taking a little slice of gasoline, because remember, when we calculate work, we have to think about dividing up that liquid. In this case, it's gasoline. We're going to take that liquid, and Trying to draw that in there. It's kind of hard to see on my picture, but we're going to take that slice and we have to think about how much work is needed to lift that slice up and out of the cylindrical drum. So that's what we're doing. So let's calculate, let's set it up. So the work for an individual slice, and again, I'll go through the theory again one more time here. So when we calculate work, work is force times distance, but force is mass times acceleration in physics principles, and mass is density, and it's density of gas in this case, times gravity. Now we remember that our density is this constant we already have over here. So the density of gas is 737 kilograms per meter cubed, and my gravitational constant is 9.8 meters per second squared. So I'm going to carry those two constants along while I am keeping my while I'm keeping the rest of my content. I actually made a mistake right there. Acceleration is gravity. I jumped ahead. I wanted to get my two constants in there. Mass is density times volume. So we do need the volume of the slice. And then, of course, we need the distance. D stands for distance. So we also need the distance. So just as a reminder of where those come from and where these constants are coming from when I set this up. So the work is going to be the density of gas times the gravitational constant times the volume of a slice, which is in terms of y because of the way we set this up, times the distance that we have to lift each slice. So this is the volume of a slice. So we need to calculate the volume of a slice, and we need to calculate the distance lifted. So let's think of that in terms of our scenario. So the work for a single slice is going to be the density of gas times gravity. Now, what is a volume? What is the volume of every slice? Well, every slice, if we look at this, every slice is this, just kind of looking at that picture right there. Every slice is that rectangular slice. So what we think about when we think about a rectangle is width times length times height. So what is the width? Well, the width of this slice right here is changing. So this is a variable slice. The slice is unlike our previous example. The slices are going to vary. The slice right at the center, the width is going to be 10 meters because 2 times the radius. But down here, the slice is going to be a little different. So what would be the slice? How would we represent that slice? Well, it's going to be 2x's. So the width right there is going to be 2 times x. But we do know, based on the coordinate system, that I could solve for x in terms of y. X is going to be equal to the square root of 25 minus y squared. So the width of each of these slices, when we look at a slice of this gasoline, is going to be 2 times the square root of 25 minus y squared. Now the length of each slice, the length is fixed all the way up the cylindrical drum. That's going to be 10 meters, and the height is a delta y. So when I'm setting up the volume of each slice, I'm going to get 2 times the square root. I need a little bit more space here. 2 times the square root of 25 minus y squared times 10 times delta y. So that is the volume of each slice, and it does change based on where we take that slice. So that's the volume of each slice. And then I need to calculate the distance of each slice. Well, how far do I have to lift each slice to get it out of that cylindrical drum? So let's think about it in terms of the coordinate system. So this piece right here is 5. This is 0, this piece. This point at the top of the drum is 5 units above the origin. The origin is at 0, and this down here is at -5. Based on the coordinate system, we have to always base it on our coordinate system. So how far do I have to lift it? Well, given any generic slice, let's call it y, this distance that we have to lift is going to have to be 5 minus y. So the distance lifted is 5 minus y. So that is the distance that we have to lift each slice. And I'm going to write d of y. That is, and it is variable again, right? Because the slices at the bottom have to go further. And you know what? You can always check to make sure it makes sense. This very bottom slice, you could actually plug in -5 for y. This very bottom slice has to be lifted 10 units, 10 meters to get out of this cylindrical drum. So if it has to be lifted 10 meters, you can see that. That's a distance of 5 minus a -5. So that would be 10, and 5 minus a -5 would give us 10. And so that is the volume to lift each slice, let's go ahead and write that all, summarize it. So the volume for a single slice is going to be equal to the density times the gravity times, I'm going to go ahead and combine a couple things here. That's going to be 20 times the square root of 25 minus y squared. We have a delta y, I'm going to put that at the end, times 5 minus y times delta y. Now, what do we have to do? Well, this is the volume for a single slice, and we want to compute the work needed. This is not the volume, sorry, that's the work for a single, to move a single slice of gasoline. How much work is needed then for all of the gasoline? Well, that's where we get to the integral. So this is going to be the work. Now we have to think about our scenario. The gasoline slices are starting at -5 and ending at 0. So this is the integral from -5 to 0. I'm going to zoom in here a little bit so I can write a little bit better. This is the work from -5 to 0. Rho times gas times rho of gas times gravity times 20, those are all constants, times the square root of 25 minus y squared times 5 minus y dy. Now I want to clean that up just a little bit, so I'm going to clean that up and show it on the next screen. Okay, that was getting kind of long and I wanted to jump forward after I pulled out the constants and distributed the square root. So here I took the square root and I distributed it to both of those terms. So I ended up getting to this integral. Now, I have made a video that has gotten pretty long here, so I'm going to pause the video here and we'll come back and we'll do another example of lifting a chain over the top of the building, or maybe lifting an elevator. We'll do a couple more examples of lifting actual objects rather than fluid out of containers. But I'm going to leave this one here. There is some integration to be done here, and I'm going to go ahead and just leave it and let you guys, at this point, we're back into this is back to chapter 8. How would I integrate this, right? This becomes a fun problem to integrate, but I won't spend the time on this video because on this first piece, so for this piece, we'd have to split this up into two integrals, and on this piece, we'd want to do a little trig sub. In this case, we'd let y equal 5 sine of theta. And on this one, we can do a nice little u sub to integrate this, where u is the interior of that root. And that is really good practice with your integration strategy. So that's why, again, I mentioned I like doing this section after we have done chapter 8 because we can practice some of our integration strategies. But this video has gotten quite long, and so I'm going to pause it and we'll come back and do some more examples. But on this guy, that's how we set up the work. ... And this chapter really is, or this section I should say of this chapter is really about getting it set up, and then of course we can practice our integration strategies once we have it set up, but those are skills from the previous sections.